our guest today is Andrew Doherty. He's a CTO of a quantum computing startup called PsiQuantum. Andrew is a theoretical physicist. He has more than 20 years of experience in quantum physics research. Andrew, thanks a lot for coming, for finding time to share with us what's going on in quantum computers and how far along we are.
Yeah, thanks very much, Sophia, and thanks for inviting me. So I want to try and give you some kind of sense of what quantum computers are, what's happening in that field, and it'll be quite different. So, my background is theoretical physics, and the vast bulk of my career is in academia. I haven't been in the Valley for a long time. So my theoretical physics, kind of a fairly long way away from software applications, machine learning, data science, a lot of the topics that you people are familiar with. And I think it's fair to say that, there are not as yet, valuable commercial applications for quantum computers, nor do they in fact exist. And so it's really like a major challenge in physics and engineering to build the first useful quantum computer. So I suppose I just want to answer some really basic questions, like what is a quantum computer, who's trying to build one, what might you use it for, and just give you some kind of representative activities that are going on, and then we can have questions and so on. So let me just see if I can share a screen. So I suppose one thing which I sort of alluded to in my abstract is there's a bit of a bewildering, I did something strange there. Hang on, sorry. I pushed the wrong button, I think. Let me just try this again. I won't try and talk while I bring up the slide. I'll just, now you should see something. And if I hit that, so that should be good. You see the whole thing, good. Okay. So what I actually did for this title slide is I literally searched quantum computers in the news on Google today. And this is just today's version. And I think every couple of weeks there's some significant significant in the sense of a high profile press release announcements. And so on the right there, IonQ is a startup company that's trying to build a quantum computer on, they're based in Maryland, and they've announced a roadmap towards building a useful device over the next several years. They announced that today. There's a sort of a quantum computing business conference that's going on at the moment. So you probably see a few of these in the news right now. And, earlier this year, IBM announced a roadmap of this kind. Google has talked publicly about a roadmap that they've been developing towards building a useful quantum computer. So that's kind of an announcement about plans. On the left-hand side, this is this week's sort of device where someone's actually built something, measured it. There's some performance that's being described. Here I feel like, to a non-expert, there's lots of bewildering claims. So here it is, this idea of what's sometimes called quantum supremacy or quantum advantage. The basic idea here is that you design a problem which has no earthly use, but the problem is something where you can estimate how much work you need to do on a conventional computer to solve that problem, and then you design the problem so that it's so big that even if you committed enormous amounts of the world's largest supercomputer, enormous amounts of time on Summit or something towards solving that problem, you would be unable to do it. And there's some relatively small quantum device that is able to achieve that problem. And so that's this idea of quantum supremacy or advantage. So this is, a device that by design has no application, but it's kind of like it's a hoop that has been designed, and there's some reasonable argument that a conventional computer could not jump through the hoop, even a very large one, even one working for a very long time. And then there is actually existing today device. So you may recall that Google announced that device. They had a 52 qubit device that achieved that kind of task last year. And there's a Chinese group that have just recently announced this. So Google's device was a superconducting device. So superconductors made metals that conduct electricity without resistance at very low temperatures. They're definitely one of the leading approaches to building a quantum computer. Another leading approach, and that's actually one that which my company is working on, is the photonic approach. So encoding information actually in light rather than in what electrons are doing. And that's what this Chinese group have built something which is demonstrating this kind of supremacy. So that's an exciting development in this sort of area just recently. But it's probably a little bit, bewildering, some of these terms like supremacy and so on. Hopefully we can chat about that if people are interested and get a sense of where we're at. So it's an obvious question is who's doing what? And I wanted this slide originally, my apologies, it's a bit higgledy-piggledy. I wanted this slide to talk about like large tech companies, which is on the left, and startup companies, which is what is on the right. And there should really be another column, which would be academic activities. So, historically, the bulk of research in quantum computing has taken place in academia and in certain government laboratories, like the National Institute of Science and Technologies here in the US. And that's still where a lot of the most creative research goes. But in the last several years, commercial activities in this area have been very important. So the startup companies, what I've put here are only companies that I understand to have some fairly serious hardware effort, as in they're building a quantum computer. There'd be some very much busier slide with people that are engaged in algorithms development, in designing control methodologies for quantum computers, and that sort of activity, which is is not nearly as expensive. What we're going to see is you're trying to build a very exotic high-end device, which is pretty capital intensive if you're trying to really build the quantum computer, really pushing the envelope of not just one technology typically, but a lot. So the right-hand side is there has been a lot of venture capital funded startup companies. Rigetti builds superconducting qubits. IonQ, who are on the previous slide, build these ion trap computers that's just sort of trapping individual atoms and using the valence electrons of those atoms to encode information. And at PsiQuantum, we work on photonic, so encoding information in what are photons doing, where basically is a photon located in one place or another indicates whether you've got a 0 or a 1. But you'll probably be aware there are really big high-profile research efforts at big tech companies. So Google, I mentioned them on the previous slide. They've got a big superconducting qubit activity, as do IBM. Microsoft has a big hardware development, as well as really a very prestigious algorithms and control and theoretical development group. Honeywell have built ion traps. They periodically make announcements. Intel are involved in this as well to some extent, and particularly one of the features of quantum computers, a lot of the materials that people want, in fact, essentially everything on this slide really requires deep cryogenics. So at least temperatures around 4 Kelvin. And for many of these devices, they're operating at tens of millikelvin. And that requires not just cooling technologies that are pretty out there, but also cryogenic electronics just for control. So things that are like conventional computer chips, but are going to operate at very low temperatures, like at least 4 Kelvin to control qubits. And Intel's been doing that. So there's several, if you go searching for their activities, they've announced several cryogenic control chips for quantum computing. Amazon, specifically AWS, is pretty clearly setting up a hardware activity. So that's a picture of like some of the people that are involved. Okay, so what roughly is a quantum computer? And so it's probably a good idea to kind of think to begin with about what a computer is. So this thing here on the left is some sort of image of the M1 chip that Apple announced in the last couple of weeks. So this is a typical, this is the most recent kind of major announcement. They're no longer using Intel chips. They've got their own chip, but that is a conventional CMOS silicon chip. And we're very good in if we're writing code, we're very good at abstracting away. It's one of the great advances of computer science to abstract the notion of information and zeros and ones and algorithm design and software and all of these things away from the physical underpinnings of the device that's processing the information. So you could be agnostic, you can swap different computing devices in and out. But, you know, as a physicist, you know, it is very important fact that there is some physical device that is encoding that information. And, you know, inside that CMOS technology, the zeros and the ones are fundamentally encoded by moving electronic charge from one place to another. So, you know, a zero could be one location for a lump of charge and a one could be a different location. But typically that is a lot of charge. So a lot of electrons in that semiconductor are moving around in order to change from a zero to a one. You know, the simplest notion of what a quantum computer is you might attempt, as researchers in Australia are doing, to basically build one out of a CMOS, a modified CMOS technology. And the difference would be that in a quantum computer, you have to be controlling what one electron is doing. So a way of encoding information would be to say, I'm actually going to put, now let me just see if I can you actually see a cursor there? Yeah. So what you're doing here is looking down at a chip from above. And these sort of lighter yellow pieces are electrodes that trap electrons in puddles. And the two puddles, one of them is kind of indicated as a red dot here, and another one is indicated over here. And so moving an electron from here to here, that could correspond to changing a 0 to a 1, like performing a NOT gate. And you know, just for scale, that's 400 nanometers. So you know, you can in these devices, you know, they're silicon devices. They're built out of the same basic materials as modern computer chips. And they're encoding using the same basic physical principle. And so the real issue is that when you start manipulating one electron, that electron obeys these physical laws of quantum mechanics. And, you know, one of the big insights that I'll talk about in a minute is that certain computational problems are just much easier if the fundamental physics of the computing device is quantum mechanics rather than classical mechanics. But the actual physical difference in the computer can be as simple as replace a device which is performing logic by moving qubits around, by moving electrons around in bulk, to a device which is performing logic by moving electrons around one by one. And then this picture on the right is showing, you know, there's a lot of electrodes which are required. So the different colors indicate different electrodes that are there for different purposes to trap these individual electrons. And then this rather big thing with, it's a magnetic field, which is indicated here, is to actually learn what a single electron is doing. If you can imagine what is the problem that I'm, you know, how do I get myself an electrical signal that's like, I can read off in some oscilloscope or something from one electron. I have to work pretty hard. And so, you know, a bit of the sense here is that although the scale is 200 nanometers, there's quite a lot of technology that needs to be brought to bear on this tiny little device, which is encoding just a single bit. You know, one thing to point out is you don't have to encode the information physically in the location of a single electron, which basically means you're moving charge. You know, like if you think about memories, you know, at least some of us are old enough to remember magnetic memories. You know, so the basic idea was you had a magnetic material and you would encode zeros and ones by which direction the North Pole of a region of that magnetic disk was pointing. So electrons are also magnetic materials. They have a north and a south pole. And again, I could take a single electron and encode information in which direction is the north pole of the electron pointing. And that could be a 0 or a 1. And I would design some kind of semiconductor material potentially to manipulate that single electron. So that's the basic picture. We're going to manipulate one electron at a time or one photon at a time, but we're going to attempt to store information in an analogous way. Why have we got something new? Well, the quantum mechanical laws, Schrodinger's laws of quantum mechanics, Heisenberg's laws, they turn out to give us a big advantage in solving certain kinds of problems. But and so that's why, you know, and then the next thing to notice is these very exotic devices that we need to build that are going to be very challenging. They may have to work in extreme environments like tens of millikelvin temperatures. And you know, I've alluded now to photons and to various semiconductor approaches, and I said Google was working with these superconducting devices, which I can say a bit more about. IonQ, which were on that first slide, they're trapped ions, so they trap atoms one by one. They're really ions, so they've ripped an electric charge electron off the atom. They've trapped those atoms one by one. They manipulate them using lasers and other kinds of electromagnetic fields. And basically the information is stored in what is a valence electron of that ion doing. Those semiconductor quantum dots are what I was just showing you. So some modified semiconductor material, could be gallium arsenide, could be silicon, similar materials to the way people build conventional computers today, but very different processing, very different scales in terms of how many electrons are you moving around and what you have to do. You can encode information if you can encode it in ions, you can also encode it in neutral atoms. That's an activity people do. There are things that look like atoms that are defects in solids. So if you've ever looked at a diamond, and some of the very distinctive optical properties of diamond are because there are these, they're called vacancy centers, basically defects in the crystal structure of the diamond that look like a localized atom that you can manipulate using lasers and other kinds of electromagnetic fields. You can encode qubits in that kind of material, not just, I've said MV centers in diamond, there's many similar things that live in solids of various kinds, including things you might have heard of, you know, in optical fiber technology, you have erbium doped glass, basically. So that kind of erbium might be something that you would try, that sort of material is something, or atomic defect in a solid is something you could try and encode qubits in. If you've read anything about Microsoft's activities in quantum computing, you might have seen this term Majorana Enion. We're getting fairly far out there, but I just want to give you the sense there is no agreement in the field as to what is the right device or material system to build a quantum computer out of. And each of these that I've listed at the moment is being very seriously pursued by some group or another. Okay, so why would you want to do it? So in the mid-90s, and this is kind of when I started my PhD, there was a lot of excitement because Peter Shaw, who's in the photograph, had really thought about solving a simple problem. And that simple problem is, how do I find the prime factors of a large number? So you know that if you have two numbers, you can do the multiplication in your head. But if I say, so if I give you two prime numbers and you could probably multiply them in your head even to quite a lot of digits. But if I only told you their product and asked you to find the two prime factors that had been used, that is a hard problem. And you know, you might almost start going through a list of prime numbers and just working out which one divides the large number that you've been given. So there are various algorithms that exist for finding the prime factors of large numbers, and they're not efficient. That is, they take more than, the amount of computation you need to do grows faster than polynomially in the number of digits of the number whose prime factors you're attempting to find. And what Peter Shaw showed, and maybe this is kind of surprising, but it's a very concrete result. You know, it is an algorithm. You can study that algorithm and you can convince yourself that you can find the prime factors of a large number using a number of operations on a quantum computer that uses the rules of quantum mechanics that scales polynomially with the number of digits. And honestly, I can't now remember whether it's quadratic or cubic, but it's one or the other. And you know, why would you want to do that? Well, many of you may know that this problem of finding the prime factors of large numbers is the basis of public key crypto system, the public key crypto system RSA, and that's, you know, that's the basis of, you know, a lot of secure communication, including secure communication on the internet. So you know, this thing at the top is it's my bank in Australia, right? So you go and you talk to your bank online. The way that you can send messages that are encrypted readily is that that your bank announces some key, which is basically just the large number, and they've generated that large number by multiplying two large primes, and then So they're able to decrypt it using those primes, and you are able to encrypt it using the large number. And any sort of eavesdropper is not able to decrypt the message because they don't have access to the prime factors on a reasonable timescale. If you had a quantum computer, then they could have access to those prime factors. So some things about that. So, that's a commercially important problem. Basically, it's at the basis of a lot of internet commerce at the moment. It's a very number theoretic problem. It's a number theoretic problem. It's a problem where it's very easy. Well, it's not very easy, but it turns out to be very easy. Like once Peter Shaw has explained it to you, it's easy to analyze that algorithm and determine that the algorithm is definitely polynomial. We don't know how good a classical algorithm finding prime factors could be. Some of you may know that primality testing itself is something which is a problem that's been around since antiquity, which didn't have a polynomial algorithm till the last 10 years or so. It's conceivable, that's typical for a lot of number theoretic problems. It's conceivable that that's true of prime factorization, but people are moderately confident that no conventional algorithm will be found that would reproduce that polynomial scaling. Now, so some other things to say, there are a lot of other algorithms in that table that are alternative applications for quantum computers that are all similar. They're number theoretic problems that have related public key cryptosystems. And the top 4 all have algorithms on a quantum computer. The bottom 2 do not, and actually potentially are not likely to. But yeah, so the main flavor of problem that we really can convince ourselves is useful and can be solved efficiently on quantum computers, it's this kind of thing. And that is what in the mid-90s caused a lot of the excitement about building a quantum computer. If you would ask me, why am I excited about building a quantum computer, and why do I think it's actually going to be really important for a lot of people's lives? We will replace public key crypto systems with versions that are not sensitive to attack by quantum computers. That's an important issue. Once you do that, it's less interesting to build the quantum computer to break people's communication with their bank. I think the reason to get excited about building a quantum computer is actually the first idea, a much older idea, dates to the early 80s from Richard Feynman, about what a quantum computer could be good for. And the basic answer is simulating quantum physics. So much of chemistry and material science, I've forgotten a really important, catalysis, industrial catalysis, for example, depends on quantum physics. And at the moment, we simulate cartoons of that in order to understand industrial processes. Materials science, if we're building planes, trains, automobiles, potentially drug discovery, all these kind of things. There's so much quantum physics in there, and the tools we have to do large-scale simulation of those are so crude that really it's going to change. It's going to change a lot when we're able to build quantum computers and sort of efficiently determine quantum chemistry, for example. Answer questions like, what is it exactly that legumes are doing when they fix nitrogen at room temperature? Can we build nitrogen fertilizers without the Haber process? That's a problem that Microsoft has emphasized as a potential application. If we could understand when does a material superconduct, can we make high temperature superconductors? That's got enormous technological implications. So that's what I think is really the application. I think there's heaps of uses for that, but the picture for that is supercomputing, specialized supercomputing to solve kind of specialized problems that are going to have an enormous impact, and could have impact on a lot of places. Fuel cell technology, like all kinds of stuff that's very important for the technological problems that we face today, and technologies people have on them, in their pocket right now and use in everyday life, making those things better and cheaper. But it's really getting to it's high-end simulation of these kind of quantum physics for materials and advanced materials chemistry, that sort of thing. I'm going to skip through these slides. Sorry, I hate this to do this to you, and you can ask some questions. Actually, I want to show you just this picture. So one of the approaches that I've mentioned is trapped ion qubits, this is just to give you a sense of the kind of academic history. So these in the mid-90s, these were one of the leading approaches to building a quantum computer, and they still are. And the person on the right is David Wineland, and Dave Wineland was at NIST, National Institute of Standards and Technology in Boulder, Colorado. He's a Nobel Prize winner for his work on developing ion traps, not only, but in large part for quantum computing. Chris Monroe worked in his group for a long period and has led groups subsequently. He is at the University of Maryland, and he's a founder of IonQ, who are the startup company that I mentioned that work on ion trap computers. What you're seeing is optical benches. So these, there's a lot of optical elements for a UV laser light that's used to shine into, now, sorry, I didn't know exactly where, somewhere or other there is a vacuum chamber, and there's a little glass cell somewhere which you actually probably can't see on either of these images. You're seeing some bulk optics. You're seeing some big magnetic coils, applying magnetic fields with electrical coils. This thing here, I think, is a vacuum pump, and this will be related to a vacuum pump. Typically, these things have ion pumps and turbo pumps. If people are familiar with ultra-high vacuum technology, this might be 10 to the minus 12 torr. One thing you can't see in Chris's photo, but you can see in Dave's, is there's still another table, like that's probably producing the appropriate laser light, with the business end of the device down here. This is a room scale tabletop experiment that's implementing a handful of qubits. And that's what research has been like in this field over a long period. We're just moving out of that period into a period where people are trying to build miniaturized, reliable, scalable technologies that you could manufacture in devices that might have 1 million qubits. Sorry, qubit is quantum computing jargon for bit, if that wasn't obvious. That's a really big challenge. So if you look at what are people announcing, Google's announcement is a 50 qubit device. IonQ has announced 11 qubit devices, and next year they are talking about releasing results from something which was from memory in the mid-20s. So if you want to say, well, what are people doing? What is the scale of computation people are doing? It's operating on, let's say, a handful of tens of bits and doing maybe 100 sequential gate operations. And our best estimate for what the first useful quantum computer would be at least maybe 1 million physical bits and maybe 10 billion sequential gate operations. And achieving that level of reliability that you can implement 10 billion gates is something we don't think about too much in conventional computers. That's because errors occur in conventional computers at just astronomically low probability, but are likely to occur reasonably frequently, maybe even one time in 100, 1,000, or 10,000 operations in the first generation of quantum computers. So that's another challenge, which is just that hardware is just intrinsically much less reliable than these modern computers, which have gone through many generations of technology development. So just to give you a sense of that picture, we've been emerging from specialized academic research into a period of commercialization, at least at the level of trying to build prototypes. This is kind of a lot going on in this slide, but I was just thinking for superconducting devices and ion traps, what is the history of this field? What is the time that's gone on? And, there's a very important development in the history of quantum physics, of controlling individual quantum systems and applying that to technology, which is if you've ever had an MRI medical scan, which physicists call nuclear magnetic resonance, but which gets called magnetic resonance imaging in the context of medicine. That was discovered in the late 40s. And a lot of those ideas that go on there are actually how we think about controlling qubits now. And that's a lot of the history of where a lot of standard techniques in the field started. There are also in superconducting devices, there are magnetometers and various other sensors that are made out of supercomputing devices. There's that Q there, SQUIDs are actually something like superconducting quantum interference devices. Those are magnetometers, started being developed before 1970. IBM was developing superconducting devices for conventional computers in that time period as well. And that's part of the history of where these Josephson junction superconducting devices for information processing comes from. Things that were happening in the 70s where people were carrying out experiments because they were interested in some specialized applications like sensors, alternatives to semiconductor computers, the measurements of the fine structure constant. Physics nerds will know there's been recently one in the last couple of weeks. This is a very important physical constant and relates to time standards. So the reason people developed ion traps was really for time and frequency standards. And then people in the 70s started to think, well, we can do some quantum physics with these devices. They're really beautiful material systems. And then people took some of those ideas in the 70s, and then through the 80s, people started to see some really beautiful quantum, you started to be able to look at what is an individual valence electron. This quantum jumps experiment, you could do an experiment, you could go into a lab, you could see a single ion flashing on and off like a light. And what you were seeing then was, with your naked eye, a single valence electron on a single atom changing from one electronic state to another. And so that was a level of control of individual quantum systems that's like a precursor to the ability to build quantum computers. And there's similar developments that were going on in superconducting devices. And then, in the mid-90s, when I started to get interested in that, Peter Shaw came along and said, look, there's really a good use for a quantum computer. That's in 1995. And the first kind of single qubit demonstration experiments, including in ion traps, also happened in 95, 96. The first superconducting qubit device was 99. That was a Japanese experiment. And then you can sort of see, 4 qubit ion traps come along in 2000. A second generation superconducting qubit device came along in 2007, which really sped up progress in that area. By 2014, there were 5 qubit devices. And then, the state of the art at the moment is this kind of like a 53 qubit device, and there's 11 qubit IonQ device. And what we are yet to see, but what has to happen is, like faster doubling times on the scale of devices that can be built. And that's going to require really demonstrating scalability in some technology. And that's like yet to occur. It's yet to happen, but that's the challenge that's in front of the field at the moment. I'm just going to skip through a handful of slides that might be of interest to people. I don't know about you, when I was young, I learned programming from these books of basic programming. And I started actually doing it without a computer. Like, we didn't have one at home. On my summer holidays, I had a notebook. And I used to write.
You are new.
I used to write, there were problems in here, write a program to do this. And I would write those programs out. I learned BASIC and I wrote the things, but I'd never touched a computer. And so of course I didn't know that you spend all your time debugging. I didn't really understand anything about either the limitations of a computer and programming or about the possibilities, because I didn't have one. And one of the things which has affected our ability to predict how useful a quantum computer is just the fact that we don't have them. Most of the way we learn about the opportunities and the limitations of high-end computer simulation is by evolving the code that we have and really understanding in practice the performance of that code. So there's a lot of answers about what a quantum computer is good for that we are not going to have until there actually is one. But there are a number of open source frameworks for programming quantum computers. These things drive emulators of quantum computers. And so those things today are either very small scale devices like 10 qubit devices, or they're computer simulations of small scale devices like 10 or 20 qubit devices. But people have really kind of worked out, like, what is a code? What is a Python style script that I can use to basically generate machine code for a future quantum computer and, get some understanding of how that works, whether it's on a cloud-based quantum computer prototype or some cloud-based emulator of a supercomputer emulator of a quantum computer, and you can pick your big tech company. So this one here, the guy called Dave Bacon, who I used to know when I was at Caltech, wrote this for Google. So if you like Google, look up Circ. Azure Quantum is Microsoft's quantum development kit. If you like Microsoft, go have a look at that. I'm sure that all of these, they've got this Qsharp programming language, and that's, I'm sure got great tutorials. If you like IBM, theirs is called Qiskit or Qiskit. I don't know. I suppose this is to rhyme with biscuit. I don't know. They've got a great tutorial there. Look up IBM's quantum efforts, and you've got that. This is not an exhaustive list. If you like Rigetti's got one. There's a lot of these out there, and like if you're a programmer and you like to think about programming something, there's some open source development kits that you can play with. Learning about quantum computing is obviously a big challenge, and I haven't shown you any equations or given you any quantum math. There's a lot of good starting points for that. I just thought I'd highlight this. Mike Nielsen's in the Bay Area. He really, when I say he wrote the textbook on quantum computing, he actually wrote the textbook that is in every expert's office. But he's been in the Bay Area for a little while. He was at Y Combinator Research for a while. At the moment, he's very interested in, actually how do you present people like in some online setting with training for these kind of difficult technical topics. So this tutorial, which is online, the idea is that there's actual work in there and you're supposed to do that work and test your attention later. And he and his collaborator are really trying to research that sort of how to do some research in basically online teaching. That's sort of part of their interest. But this example here is quantum computing. That would be a great place to start to learn some stuff. Oh, and that was the end. Okay, so that was my last slide. Thanks very much for your attention. I hope that was kind of interesting. I rambled for longer than I planned to.
It's totally fine.
So if I asked you to give me that 20-minute warning, it just didn't.
No, it's great. Thanks a lot, Andrew. So we have several questions. I see a question from Son Pham. Actually, guys, you can unmute yourself and ask Andrew directly if you wish. So Son's question is, doing quantum computing as a service if devices are so specialized and expensive? So
yeah, that's right. So I think that is the obvious. So let's say, early quantum computers will be specialized, they will be expensive, and they will have to solve kind of high value problems like, what's the right catalyst to try and do room temperature nitrogen fixing, things like this, or advanced materials for cars or planes, problems where, investing quite a lot and getting the answer to that problem makes commercial sense. That would mean, I think, by and large, that there will be cloud-based. One model which I know people are thinking about is, that someone is producing the hardware, and on the cloud they're serving that. They're serving the quantum computer. And you can actually see that if you start researching some of these groups that I've told you about, people are putting quantum computing prototypes in the cloud already. IBM's quantum experience has been there for some years. It's actually fantastic. It's a fantastic resource. If you're friends with any high school kids that are interested in this stuff, they can start programming IBM's prototype device on the quantum experience. It's fantastic. It's a 10 qubit, 20 qubit device. You could simulate that device on a laptop, but it's pretty, you're actually implementing, they run their hardware in something like real time in the response to what people are doing. And you'll see Amazon and Microsoft, Microsoft is got this Azure Quantum platform is actually going to allow you to work with more than one quantum computing prototype that's in the cloud. So absolutely, I think that the main, your default expectation would be that people are going to build some large specialized supercomputer. It's going to be a quantum supercomputer. It'll be available over the cloud, and only very specialized users would want to buy it for themselves, although I'm sure that would also happen.
So Nirich is asking, are there any significant computational differences between those different types of qubits, like photon, trapped ions, and so on and so forth?
So the answer should be no. So it should be just like, so in, I said this before, the great advance of Turing and computer science in general is we don't have to worry, that it should work much the same no matter what the hardware is. And things that are efficient on one computer should be efficient on another. And so that will also be true of quantum computers. So the question about these different materials is really which one of them provides the most natural means to building, to manufacturing a large-scale device that's actually going to be useful. And because because you're really pushing performance, you're operating in an extreme cryogenic environment typically, and then you're also trying to push pretty much every performance spec that you could imagine relating to these materials. The question of what really is a manufacturable solution, everyone thinks their own approach is manufacturable. So of course, I'm going to tell you that photons are the way to go, and I could tell you why, but like others are going to have very good reasons for arguing in their own corner. But that's really the reason to investigate different ones. I would say that, at some point you would imagine that you want to network different quantum computers potentially at a distance, or connect them up to provide in something like a cluster. And it seems natural to imagine that that would involve optical fiber communications. So you potentially, potentially a photonic qubit would be useful to send over optical fiber between computers that are potentially not using photonic qubits. So certainly there could be a call for different materials depending on the application. If it's communication more than just or networking in one way or another more than just the computer device itself. But broadly speaking, they all should work the same in the end.
I have a quick follow-up on that. So you mentioned that like something like 1 out of 10,000 instructions will be corrupted. Does that have anything to do with the materials that you mentioned, or it's just a theoretical kind of? Yeah,
no. So that 1 out of 10,000. So those numbers come from the materials. So you will find those numbers being reported very differently. And 1 out of 10,000. So I think roughly speaking, for operations on a single qubit in an ion trap, you can approach that 1 out of 10,000 level. It is much more typical, and you should think about memory operations, readout operations, as well as logic operations. Typically, logic operations on individual qubits are much more accurate than logic operations on 2 qubits. It is very typical of present-day prototypes that at the very least, measurement and 2-qubit operations have more like 1 in 100 failures than 1 in 10,000.
Andrew, also like follow-up question. So currently people are betting on different approaches like photons, trapped ions, but eventually only one approach will be kind of major one, or there could be like several widely used approaches.
So I think, and actually this goes back to, IBM was very involved in the 80s in developing superconducting devices for conventional computing. And the reason they were doing that is they kept on anticipating that building finer and finer scale silicon would not be practical. At some point, silicon chips, at some point, if you wanted to keep doing Moore's law, if you wanted to keep having faster chips with more capacity, that basically there'd be fundamental physical limits to the processing that would prevent you from doing that. And there were various good reasons that superconducting devices were under consideration in the 80s. And then, well, silicon just kept getting better, and we don't buy superconducting qubits, even superconducting computer devices, even for supercomputers. there's actually been a resurgence in interest in that kind of work recently, because people again are of the view that, and it's just got to be the case that at some point the semiconductor physics will prevent, people are talking about 5 nanometer chips. That's what Apple is calling its M1 chip that I just showed you. So it's like the feature size on that chip. Once that thing is a 1/10 of an angstrom, that's the size of an individual atom. Like, surely you can't do better than that. So at some point there is a physical limit So the point would be, sorry, that's a long answer. My point is, if we look at conventional computers, actually many things, there have been vacuum tubes, there have been superconducting devices. If you go back to the sort of vacuum tube age, people were looking at many different things, and transistors and silicon particularly, there was germanium, there were various other semiconductor materials. Many things were investigated seriously, but when one proved to be by far the best, everyone started using that one. And I would imagine that that will be what happens, unless, as I said, I think modulo what I said about networking and optics. Because again, that's the communications technology we have at the moment. I think there's likely to be a call for optics, but I expect that this kind of many layered approach, everyone's got their own favorite, will narrow down when one is definitely better. And you see that within these approaches as well. If you start looking in the literature on any one of these, like particularly semiconductor devices, you'll find that every research group has its own way of designing qubits out of semiconductor devices. That used to be true of superconducting qubits as well. But that second generation transmon device I pointed to has basically convinced everyone. And I think at this point, almost all groups are pursuing something which looks like that particular technology. So I think the history of the field, the history of quantum computing, the history of conventional computing says it will narrow down when one is definitely shown to perform better in some respect.
Mm-hmm. So another question from Niraj, is there a notion of quantum computability, which we know to supersede the Church-Turing notion of computability?
So this is outside so I should say, this question you're asking, this whole idea of Turing, is a question of theoretical computer science. And people who think about computational complexity, questions like P not equal to NP, computability, and all this kind of thing. Some of the world's best theoretical computer scientists have spent some large fraction of their time in the last 20 years thinking about quantum computer science and exactly the sort of question that you're asking for. Now, I am not an expert on that stuff at all. What I can say is, this question of computable and uncomputable is independent of whether you have a quantum computer or not. So uncomputable things remain uncomputable, computable things remain computable. The difference actually, in computational complexity, the class of problems that are regarded as efficiently solvable are called in class P for polynomial time. That means that the amount of computation should scale polynomially with the problem size, the number of digits in the case of prime factorization. So what Shaw showed is that the problem of finding prime factors is in not the class P, but the class that gets called BQP, which is called bounded probability quantum polynomial time. So, naively, you would think that the class of problems you could solve efficiently on a quantum computer should be called QP for quantum polynomial. But one of the things that I managed not to mention about quantum mechanics, but which you probably know, is that it predicts the probabilities for certain things to occur, and events don't generally occur with probability 1. So you're doing something that's more like probabilistic computation. And so there's always the chance when you run a probabilistic computer that it refuses to give you the right answer. So that bounded, with some bounded probability, you want to get the answer and you want it to be right. And then you want to do that, you want to get to that point within polynomial time. That's why the complexity class is called BQP. And the conjecture is that certainly, so the first thing, the thing we know is that there are problems like prime factorization that are in BQP, so they're efficient on quantum computers, that are not known to be efficient on classical computers, that is, they're not in P. And so the conjecture is that BQP is bigger than P. If you know anything about theoretical computer science, you know that it's very difficult to actually show that any problem is actually hard. So we believe that quantum computers have different complexity classes than classical computers because we do not believe that it's easy on a conventional computer to find the prime factors of large numbers, right? But that's a belief based on thousands of years of trying to find better algorithms. It's not proved. But so long as you're willing to believe that finding prime factors is a hard problem, then what that's told you is that quantum physics has changed the complexity classes down below. So everything to do with complexity classes is about computable problems, but the things that are efficiently computable, there are more things that are efficiently computable on a quantum computer than on a conventional computer. And so it definitely changes quantum complexity theory. It modifies what's called the Church-Turing thesis because there's this thing called it modifies what's called the strong Church-Turing thesis, which basically said that all sort of whatever physics you designed a computing device out of, it would look like a Turing machine. That turns out not to be quite right. It would be that whatever physics you build a device out of, it might potentially look like a thing called a quantum Turing machine. Quantum Turing machines can efficiently solve things like prime factorization. So it does modify that strong version of the Church-Turing thesis a bit, but yeah. Okay, another long answer, sorry.
Thanks a lot, Andrew. The next question, is there a reason why PsiQuantum researching in photonic quantum computing?
Yeah, so the biggest reason for that, and I should say, I mean, if you Google us, you'll find a bunch of stuff online. We are a stealth mode company, so I will be a little cagey. But the reason definitely relates to that problem that I was talking about at the end, which is how do you reliably manufacture large devices? And, I think we've been convinced, and now you see it in everyone else's rhetoric, that you're going to need 1 million of these physical qubits, not a few hundred or a few thousand. So we have a general approach, which is to try to use as far as possible, mature manufacturing processes like CMOS processing, where there's just enormous performance from things you can build at a large scale reliably. And so when you start looking at it like that, there's this fantastic technology of silicon photonics, which is you can build optical devices on conventional silicon chips. And you can hope to get those to operate with high performance electronic control circuits. And you can operate them at a higher temperature, which leads to all kinds of advantages than some of these more exotic qubit approaches. So that's our, our approach is to try to make progress on this kind of manufacturability problem by as far as possible repurposing manufacturable technologies for quantum computing, rather than trying to build a new manufacturable technology out of a material where there are currently prototypes. And I should say that if you look at really prototypes for quantum computers, there are a bunch of ifs and buts and ands, but there are a lot of very convincing, 2, 3, 4, 5, 6, 7, 8 quantum computing prototype, 8-qubit quantum computing prototypes in photonics. So that game is also, there's a lot of evidence that photonics are a great basis for accurate quantum computing, including that Chinese result I was pointing to at the beginning of the talk.
So question from Sam, how many years of education and understanding of quantum computing does it require for a person to know when a certain problem prefers quantum computer to solve?
Oh yeah. Okay. So this, and I sort of alluded to this, my firm belief is that we will best know what problems a quantum computer can solve when we have a quantum computer and we can write code for that quantum computer. And, if you talk to people, the thing to think about is like, there are a lot of people in technical computing who program supercomputers and profile their code and really understand what's going on. And when they tweak, there's many different alternatives algorithms, and they look similar on paper, but many of them perform better in practice, and then you evolve them, and you get to check how accurate they are because you can actually look at the simulation convergence and all this stuff. We can't do any of that. Like, there's none of that we can do at the moment. So I think that's one of the obstacles to this. And when the quantum computer exists, I think that knowledge of that kind of knowledge of how to manipulate data and write code on a large scale, and the skills that people have in scientific computing and simulation and modeling these days, people who do climate modeling and many other sort of analogous things that use enormous amounts of computational resources, those people will be very well placed when these computers exist. At the moment, though, yeah, you do need a training in quantum computing, and I would actually argue it's even a bit worse than this. So the things where it's easy to convince yourself that the quantum computer can solve it efficiently is where you can prove what the running time is, and that is not typical of any kind of piece of scientific computing code that gets written, or those of you in doing data analysis or whatever. You would never sit down, write down an algorithm, and then without writing a line of code, write a proof that tells you how many arithmetic operations there are in your machine learning code, right? you would write the code and you'd profile it and work out how long it was taking to run. Certain kinds of problem classes are well suited to proving how efficiently they run. And those have, it seems, I mean, so amongst those are these kind of number theoretic problems, right? And so the issue with that, and actually, if you wanted to get into that field, I would say it's almost like the quantum mechanics you need to learn. Once you know linear algebra, that quantum mechanics can be learned relatively readily, but number theory is a notoriously mathematical topic. And so there are people, the people who have made the most progress with that, so I mean, there's Peter Shaw himself. People really have almost like pure math backgrounds, and pure math backgrounds, people who've worked in theoretical computer science. The odd physicist, this guy called Alexei Kitaev, who's very important in the history of that kind of algorithm, who's just happens to be one of the best theoretical physicists around. And he happened to know a lot of this stuff. Somehow through the appropriate Russian PhD training. So I would say actually there are very high barriers to that kind of research, but they're not so much in the physics. Now, I think a lot of quantum algorithms research relates to the kind of quantum simulations that I was describing, quantum chemistry simulations, quantum material simulations. And there, I think you get, that's again, a specialized topic. You can look up the people that are doing that. And, we've got teams like that in our company. Google has teams, Microsoft has teams, IBM have teams of people that do that. And yeah, typically those people have done PhDs in actually in the field of quantum computing typically, or PhDs in quantum chemistry, conventional kind of chemistry PhDs, but it's typically, they've come from either a physics background, in fact, usually a physics background, they've gone to grad school in physics and they've actually worked on quantum computing algorithms and so on in that context. And they're pulling together like a bunch of intuitions about quantum physics, a bunch of knowledge about how computer simulations of quantum physics are done at the moment. Then they need to learn a whole lot of, whatever the application area is, whether that's quantum chemistry or material science. So it is actually quite challenging. Yeah, if it's any consolation, yeah, typically the most productive people in that kind of work are in the last few years of grad school and postdocs and so on. So it's young people. It is possible to get into it. It's not a long history, super long history. It moves very rapidly. It's a very exciting field at the moment. If you look at what are the number of consecutive gate operations required to solve an interesting quantum chemistry problem on a quantum computer, there are specific problems where every 6 months it's 10 times faster, so it's very exciting.
So question from team, are there algorithms that are known to be unaffected by quantum computing?
Yeah, so I think the main thing that I would say is, so I think the answer is kind of no. I mean, potentially there are a lot of different speedups that are known for different reasons, and I say I'm not an exact expert, and it's quite possible you could probably get some small win on a lot of algorithms if you don't ask for that win to be exponential. So, if you're willing, a very common thing that happens for certain kinds of, a common thing to think about is things like the traveling salesman problem. So, very difficult logistical kind of problems, which are what are called NP complete problems. So these are things which really we don't believe will ever be efficiently solvable on a conventional computer. We also believe that they will not be efficiently solvable on a quantum computer. So that's a sort of a negative side, but it's very common for certain problems in that class to get some kind of square root of n speed up. So maybe the number of operations is the square root of what it would be on a conventional computer. And if you're an old school complexity theorist, that's like not changed anything. But in practice, it's scaling better, but it's still inefficient. So yeah, I would say that not a lot is known. Like very little is really understood. Like if the question were, do we know anything about what kind of problem can be sped up? Well, I've given you 2 classes that I think we know, but other than that, I mean, there's very little intuition. There's a lot of people that have gone out looking for algorithms for certain problems and not found them. There's like, it's just, I think we don't have there's a lot of argument in the literature about what properties of quantum physics really speed up calculations. That's a very obscure, there are a lot of pat answers that you'll see out there, but actually, I think the answer is the experts don't agree at all and it's totally unclear. So I think it's very hard to say for any given problem, will there be a speed up? How big will that speed up be? Are there problems where we know there won't be? I honestly don't know the answer to that, but I kind of think it's unlikely. One thing we're fairly confident of is that it's very unlikely that something dramatic happens, like suddenly you can solve traveling salesman efficiently. That is very unlikely.
For that answer.
Go on.
No, thank you for that answer.
And Andrew, the next question is from Lucy. It's about PsiQuantum. So I don't know if you can comment on this. So she's asking how PsiQuantum uses single photon detection.
Yeah, well, so the key, with any photonic, with essentially any photonic approach, and these are described in the literature, you can sort of look them up. There's a really important component of that technology, analogous things are true anywhere. If I'm going to encode my zeros and ones into a photon is in one place or another, when the photon arrives at the end of the computation, I want a detector that reads out and says it was in one place or the other. And that means I need a detector that registers a single photon. And so anyone who wants to build a photonic quantum computer needs to do that. And actually such things exist. A slightly more complicated thing that you have to be able to do is you actually have to be able to register that you didn't have a photon, that you had one photon, or that you had like 2 or more photons. And so that's called photon number resolution, or photon counting. So you actually need to be able to distinguish that you've got 0 or 1 or 2 photons. And that is it's anyone pursuing photonic quantum computing is pursuing single photon detectors. That is the reason actually why you need cryogenic. That is kind of the only reason why photonic quantum computers will need cryogenic environments. So there are superconducting devices that are used to detect single photons. They're what are called bolometers. They measure heat. The superconductor absorbs a photon. It gets heated up. It stops being superconducting, which means it develops a resistance. And if you turn on a resistance in an electrical circuit, suddenly you will get a blip, a transient electrical signal. And that transient electrical signal is what you read out. And so what you're trying to do is try to set this device up so that even a single photon makes a chunk of superconductor go resistive and generates a measurable electrical signal. And such devices exist in various superconducting materials. they're being pretty pursued by quite a lot of groups for quantum computing and for other applications.
So actually, there's another question. Is PsiQuantum hiring at the moment?
Yeah, so I think we're always looking for great people. And so if you go to our webpage, there's a we're hiring, and you can inquire about that online. Yeah.
Okay, cool. So Lucy, another question.
Can I ask a question actually based on your last answer, Andrew? So it sounds like you still need to, you're basically like reading the resistance off of your detector to understand whether like it detected a photon or not. So, okay, mathematically speaking, you're still using like the movement of a bunch of electrons, or like, in order to, right? So I'm just curious about the equivalence over there.
Yeah, so the point would be, so I mean, this is always one of the things. So we encode the information during the computation in what is one electron or one photon doing. But in order to actually get a readout for the outcome of that computation, well, I'm going to need to generate a conventional electrical signal. And in all likelihood, it's going to feed into totally conventional electronics. Indeed, the input is going to be in totally conventional electronics. Like that, there's going to be a script that looks a lot like Python or something, that like I was just showing you. That script is going to generate some machine code. That machine code will be a series of conventional electronic control signals that go down into the cryogenic environment and manipulate whatever physical system it is that is moving those qubits around. And then at the end, there is something has got to convert that signal back. And actually, one of the reasons I like photons is, this is intrinsically a hard problem, right? So you can work out how much energy is there in a photon, say an optical frequency photon. And you've got to take that and convert essentially all of that energy into the energy in some electrical pulse and say to yourself, is that a measurable electrical pulse, right? And a lot of these superconducting devices, they generate microwave signals. Those microwave signals tend to require very low temperature environments, so that so that the energy of an individual quantum, if you like, the energy of an individual microwave photon needs to be larger than the ambient temperature, and so that immediately gets you to some sub-Kelvin temperature, whereas even at room temperature, a photon is much more energy than the sort of ambient KT, and so this problem, photons actually deposit a lot of energy in your detector, relatively speaking, which is why it's a relatively easy task to generate a detector that produces a measurable conventional signal, which definitely moves a lot of electrons around out of a single photon. But that's really one of the key problems. Both at the input and the output, you need to have some way of really manipulating this very fragile individual photon or electron, and then generating a signal from it, and then having neither of those arms coming in from the outside world wreck the quantum mechanical behavior of the system. And that always leads to competing design kind of requirements on the device itself.
Awesome.
Is the trick to stopping, sorry, do you mind if I ask you more questions, or if you have to go, it's
Go
okay.
for it. We'll probably have to wrap up soon, but go for it.
So is the trick, I mean, like, what's the fundamental trick to like preventing the, having those bunch of electrons having to move around, becoming like a bottleneck towards actually getting the benefits of doing quantum computation? Is it just that you have like multiple detectors running in a row, and then you just try to encode some quantum circuit or something so that you can just do one reading across all of your detectors, like at the end of the quantum computation? Is that how it works?
Yeah, so it works in different ways. Certainly, yeah. So a thing you could do if the hardware was reliable is, you would run all your gates in sequence, and then at the very end, you would turn on some measuring device and just read out a bunch of zeros and ones. Now, unfortunately, I mentioned that hardware is not reliable, and I didn't ever say the word error correction. If anyone's learned anything about cellular communication, for example, had a conversation in a rain shower, what you hear is the cell algorithms trying to increase the level of error correction in order to recover from this sort of background noise. You have to do that kind of error correction inside the computation on a quantum computer, because there are probably logic elements in there that are going to fail one time in 100. And you need to be able to get to the point where you can do an arbitrary number of logical gates by just, so typically what that means, is that in fact, you prepare your qubit, you do a handful of operations on it, and then you measure it. And then that measurement outcome is actually telling you, parity checks on that measurement outcome are actually telling you about errors that occur and that tell you how to correct those errors or how to interpret other data that you have that actually relates to the logic that you're doing. And so there will actually be a lot of redundancy in the first quantum computers in order to do this error correction. There'll be a lot of extra measurements. Those measurements will be used to create parity checks that will allow us to correct for things that identify and correct for things that have gone wrong in the computation. And one of the upshots of that is that actually what you really do in the computer is you prepare your qubit and you reset it to a 0 state. You run like just literally a handful, like maybe 10 operations. That number of operations doesn't scale with the size of the computation, then you read it out straight away. And that whole thing is just part of this redundancy and regularly reading out errors. So no qubit actually has a lot happening to it, because if you did that and it's going to fail one time in 100, I mean, you can't do 100 operations. Like you have to do a few tens of operations and then reset the thing. And so they're actually going to read out all the time.
Okay. Thank you. Thank you, Andrew.